let's recap briefly where we left off last class. And the idea here is that a molecule within atoms has either 3n minus 6 unique vibrational modes, which we call normal modes. Right? A normal chemist would call these vibrations. Right? The way we mathematically model them is through this normal mode analysis. I'll talk just briefly about that in a second. But these are the vibrations. You guys in organic chemistry, you learn for organic molecules, they've got the CH stretches and the CC stretches and the bends and all of that. Right? These are the normal modes of your molecule. And these are for what I would call uniquely three-dimensional molecules. Right? And I want to, this is general for three-dimensional molecules. And what I mean by that are molecules that aren't lines, linear molecules. Because for linear molecules, you only have 2 degrees of rotational freedom, so you have 3n minus 5 modes for linear molecules. Okay? So that's just an issue because cylinders, think of linear molecules like a cylinder. Cylinders only have 2 degrees of rotational freedom. You can rotate the cylinder like this. You can rotate it around its axis, and that's it. So there's only 2 modes of freedom for rotation, not 3. That's why we have the 5. So what I want to do today is actually look at these modes. Okay, I want to look at what's actually happening to the atoms as they displace along these normal modes. And it should be important to think about what do these look like quantum mechanically. Right? What does this normal mode, what we call the normal mode decomposition, look like? Right? And what we came up with last class was that normal mode, that each mode represents a motion of atoms that is collective, which means that all the atoms move together in some way, and can be modeled by a one-dimensional harmonic oscillator. All right, it's kind of hard to imagine what I mean by a collective motion. But we'll see it when we get to examples in a couple of minutes. What I mean by these collective motions. It means that when you vibrate, right, the idea is that a three-dimensional molecule has 3n minus 6 unique coordinates that are linear combinations of all the atomic coordinates. So there are these unique trajectories the molecule can move along and vibrate that are independent from all the other ones. Okay, so they're all uncoupled, right? Remember we talked about how when you stretch atoms away from each other independently, their motion affects the motion of the other ones. So each of the atoms, the vibrations of each bond are coupled to each other, and we want to get rid of that coupling because we don't want to think about things in multiple dimensions. We want to think about things in one dimension, right? We want to write things as a function of one variable, right? And these normal modes are these variables, right? These are collective coordinates that are unique combinations of all the atomic displacements that give us the properties that we want. Okay? The classical version of this, there's a classical analog to this, and this is what you see in drums, for instance. You can do normal mode analysis in acoustics, and drums are a great example of a three-dimensional or two-dimensional harmonic oscillator that has these normal modes. And the way you can see that is depending on the size of your drum, the stiffness of the membrane of the drum, and where you hit the drum gives you different timbres. Right? Small drums give you a different sound than big drums. The brass, the John cymbals, right? They give you that high frequency ringing because they're very, very stiff, right? They don't flex a lot because they're copper or brass or whatever. Right? You hit them and they give you that high-pitched ringing, right? They're a stiff membrane, they have a high force constant, and therefore they give you a high ringing frequency. But, you know, big drums like you have in a drum line, they give you really, really low frequencies because they're the membranes that you're hitting, the drum heads that you're hitting are very loose, and they're also very large. Right? So the frequencies, the unique modes, the unique timbres of a drum can be represented as normal modes. It's the exact same concept. They're unique frequencies that are dependent on the geometry and the stiffness of the membrane or the drum that you're hitting. Okay, so molecules work exactly the same way. Instead of thinking of it as hitting a membrane, now we're just vibrating lots of bonds, and there's a unique set of vibrations that give you these unique timbres that, of course, are dependent on the stiffness of the bonds and the atoms that are connected to them, as well as the lengths. Right? So again, the idea is that you're beating a drum or you're beating a molecule and they respond in a similar way. The difference between a drum and a molecule, of course, is that a molecule is quantum mechanical. A drum you can hit with any energy and it'll vibrate, right? But a molecule will only vibrate at specific frequencies or specific energies, right? The energy levels are quantized. Right? So the big idea is that for a molecule, the total energy of the vibrations is going to be the sum of the energies of each of the unique normal modes, the vibrations. So there's 3n minus 6 of them, so the total energy is going to be the sum of the energies of each of the modes. Right? And how do we calculate the energies of the modes? Well, they're harmonic oscillators. They look like diatomics. They're a function of a single coordinate. So E sub k, which is the kth mode, is equal to h bar. It has a unique frequency omega k and a unique quantum number v sub k plus 1/2. Right? And of course wk, the frequency, is associated with the square root of the force constant for that mode, which we called F. I'm sorry, I called it F last class. F sub k, the force constant, divided by some effective mass, the reduced mass. Okay? And so, again, everything's exactly the same as it was for a diatomic molecule. It's just that we have 3n minus 6 of these now. They're all independent of each other. They can all be excited independently. But they all act like, in terms of energies and harmonic oscillators, they all act like one-dimensional harmonic oscillators, like little diatomics. Right? It's just that now the coordinate's not just a single bond length, but a linear combination of all the bonds and all the atoms. They're all moving collectively in a unique way. Okay, so the analysis that we have to do is at least at this limit, the harmonic limit, low energy, everything looks like a bunch of diatomics, right? We don't have to do any new math. All of the previous math we did for diatomics applies here. I mean, you can imagine, though, that as we start to get higher and higher in energy, there's more and more vibrational modes all around the same energy of all of these levels, all these different vibrations of about the same energy, and things start to get complicated, right? Things will break down, right? But we're not going to worry about that. Right? They break down for the same reasons that the harmonic oscillator breaks down for the diatomic molecule. So again, the analysis is precisely the same. It's just now we're dealing with things collectively over a large molecule instead of just one bond. Okay, so let's look at some examples. And I need Sean for this in just a minute. So the first molecule I want to look at, I have 3 molecules to show you today. 2 of which I have just drawings and Sean to do some interpretive dances for us. And then I'm going to show you a more complicated example from my research about these normal modes. The first molecule I want to look at is a linear molecule, carbonyl sulfide, which is my favorite linear molecule. It's isoelectronic with carbon dioxide, except we have a sulfur instead. So it's O double bond C double bond S. All right, OCS. It's a lovely molecule. It's a Only mildly toxic, and it smells like rotten eggs. It's got a great smell. It's great to prank your friends with.
Wait, is it carbonyl sulfide?
Yeah, carbonyl sulfide.
Okay,
Yeah,
carbonyl.
Yeah, carbonyl sulfide.
All right.
You got it. Yeah, you're right. Thank you. We call it OCS lovingly. OCS. Unfortunately, it's a very hard molecule to buy nowadays, but it's a nice one. All right, and OCS again has. Let's calculate how many modes it has. Right, a very simple formula for that. There are 3 atoms. Right, and because it's linear, we have 3n minus 5 modes. Right, and so n is 3 here, so that's 9. 3 times 3 is 9, minus 5. So there are 4 modes, 4 vibrations. Okay. Now, there's no real a priori way for me to look at this molecule and tell you what the modes are. Right? It turns out there are patterns that you can come up with. I'm not going to talk about those patterns. If you take advanced inorganic with Dr. Polanco or someone equivalent, he often talks about this analysis where you can find patterns in molecules, and molecules of different types of symmetry exhibit vibrational modes that are common. They're in common with each other. So molecules that look similar vibrate similarly. Okay, and so there's ways to come up with qualitatively what these vibrations look like. But the way I do it is I just calculate it with a computer. Okay, there's software available for free and paid software where you can plug in a molecule and ask it to calculate the vibrational modes in it, and it calculates them for you. All right, and I'll show you an example of that on my third molecule. All right, so I get these from. Of course, you can also figure these things out from the analysis of the vibrational spectrum, which is what you do in the third rotation in the sulfur dioxide lab. We'll actually be able to identify these vibrations for sulfur dioxide by looking at the way that the spectrum for each vibrational mode looks like. The shape of the absorption gives you some information about the type of vibration that occurs. All right, so we'll see that in lab, and I don't want to focus on it too much here because it's not super important in the sense that it confers essential ideas about the vibrations. But you will explore them in lab. So, Sean, if you don't mind. So I'm going to have Sean today for the next 2 molecules. He can't do the third one, as you'll see in a second. Talk about the. Maybe we'll try it just for fun. All right. So I'm gonna correlate the structure to Sean's body so we can see how these things move. All right. So I have OCS. And the way I'm going to correlate that to Sean's body, here's Sean, here's his little hair, though his hair is much neater now. He's got this, we'll give him a nice smile. And we'll give him some wheelies.
Those look like high heels.
Okay, we give him some stilettos. And we're going to make his right hand, or from your perspective, the O, his head the C, and his left hand the S. Okay? All right, and he's going to show you these normal modes that are these collective motions of all the atoms. And there are 4 modes. And what I'm going to do is I'm going to list them from highest energy, highest frequency to lowest. And we notate them this way in chemistry. So we always call the highest energy mode or we label the highest energy vibrational mode in a molecule by the label nu1. Nu1, V1. All right, so the quantum number label, if you will, remember V plus 1/2, we would say this is V sub 1 plus 1/2. Right? And the nu1 for OCS, or really any molecule that's linear, is what's called the asymmetric stretch. All right, and the energy of this for OCS is at 2174 wave numbers. Okay, so if we had a tank of OCS and we made a little gas cylinder and put any air upstairs, you'd see theoretically we'd see a nice peak there for this absorption. We'll ask the question whether we actually see it or not in a second. And the reason why it's called asymmetric stretch is that the 2 double bonds in a molecule are stretching in opposite directions. Right? So in this case, the O stretches out and the C stretches inwards. Right? And remember, in a normal mode, the center of mass can't change. It has to stay constant. That's our assumption, is that the center of mass is always at the origin. So the carbon also has to move a little bit because this sulfur has more mass moving this way. The oxygen can't counteract it nearly as much because it's half the weight. So the carbon also has to move with the oxygen to counteract. Or sorry, the carbonyl has to move slightly in this way to counteract it, right? So you want to get that shit right. It's just like this, exactly. Right? And this has this is the highest frequency, 2174 wave numbers. As we'll see, this is very, very similar to most C double bond O stretches, carbonyl stretches. The next molecule we'll look at has a carbonyl, and you'll see that the primary stretching of the CO bond tends to fall in this 2000 wave number range. Right? That's just kind of a characteristic frequency for these kinds of bonds. All right? And of course, the next question we have to ask is that, okay, so there's some energy level difference of 2100 wave numbers roughly between these two levels. If we shine infrared radiation at them, do we see an absorption? And remember, the thing that has to happen in order for an absorption to be visible is that the dipole moment of the molecule has to change upon vibration. Okay, and in this case, in this molecule, oxygen is more electronegative than sulfur and more electronegative than carbon. So most of the negative charge is pushed towards the oxygen. So we often draw it like this. This is the dipole moment of the molecule in this direction. Okay? And so what happens, and remember the dipole measures how the extent of how the negative part of the charge distribution is extended from the positive. Okay? So if the charge distribution gets more compact or extends in some direction, the dipole changes. Okay? So it's very clear if you think of this. If the O is like partially negative charge here, and we can say this region is kind of partially charged, positive, this negative charge is getting further away, and this carbon and sulfur are moving together, so the distance between the negative pole and the positive pole is changing. All right, so the derivative of the dipole with respect to the displacement, Q1, evaluated at equilibrium, is not equal to 0. All right, the dipole changes as we move along the normal coordinate Q. Okay? So this is an allowed transition. This would be, in fact, it's intense. It's an intense absorption. Because not only does the dipole change, this CO group is very electron withdrawing. There's quite a bit of negative polarization on oxygen, so when it moves, the dipole changes a lot. Okay, so it's very strong. Right? And this analysis is universal, right? Anytime I see a motion, I just have to ask the question, how is the dipole moving? How is it changing as I move the atoms? And if I'm moving atoms in a way that doesn't change the dipole that much, then the intensity of the transition is going to be very weak. It doesn't matter whether, all I care about is whether it's 0 or not. Right? We can worry about how intense it is or how strong it is another time. But in some ways, you just want to ask a yes or no question. And here it's very easy to analyze it. It's yes. It's an IR active, or it's an intense absorption. So let's try the next one. The next mode, nu2, is called the symmetric stretch.
Is that supposed to be V2 or is that supposed to be?
It doesn't matter how you write it.
Okay.
I will alternate between the two. Okay. That's just me being lazy. Either one is okay. Either nu or V is fine. All right, so the symmetric stretch is much lower energy. It's at 874 wave numbers, which is right on the edge of the lower energy side of an IR spectrometer. Typically, IR spectrometers run from about 4 to 3600 wave numbers, 400, 3600 wave numbers. This is right on the edge. In fact, you could barely see that. You can see this line in our instrument and our gas cell that we use in PChem upstairs, but just barely. And by the name, it should be obvious what this looks like, right? If this asymmetric stretch brings the sulfur in, then the symmetric stretch should bring both of the O and the S out. Right? And that's exactly what it does. Right? This goes out this way. The carbon also moves a little bit, and then the sulfur stretches out this way. Like that. Right? The symmetric stretch. And of course the dipole changes here. The atoms are getting farther apart from each other. Right? The poles are extending away from each other as it stretches. The dipole gets bigger, just naturally. Right? The dipole is a function of the distance, linear distance. So the further the atoms get away, the poles get away, the stronger the dipole. So this is also intense. Okay, really, really simple. So now we have two more modes left. And now we're getting into lower energy modes. In fact, this is starting to get to the limit where you can really take an IR spectrum without special equipment. In fact, we could not see this one upstairs with what we have. And the interesting thing about this, I'm going to group the last two together, is we're going to find out that these two modes, nu3 and nu4, are the same. I'll explain what I mean by that in a second. So in fact, they're what we call degenerate, means they have the same energy, but these are the bends, the bending modes. Okay, and there are two of them. And it's not too hard to see why. Oh, let me change my orientation. I apologize. I have the S on the right. Okay, the bend modes are pretty obvious, right? We're going to bend away from linear, right? So there's one that looks just like what he drew, what he's signaling, right? Where the O and the S bend upwards, and the carbon bends downwards to compensate for the change in the center of mass. But there's an equivalent motion that you can do that's in a perpendicular direction. It's an orthogonal motion, but it's precisely the same motion, right? Where the oxygen and the sulfur come out of the plane of the board, and the copper goes into the plane of the board. Right? These are the same exact motion, right? OCS is a cylinder, right? So bending it this way versus bending it this way, you do the opposite one to me. Yeah, there we go. Right? Exactly the same motion. It's just in two different orthogonal directions. So the coordinates that are changing are different, right? This one, the X and Y coordinates are changing, but the Z's are staying constant. Z's out of the board, but the Z's are changing here. So these are identical, and so we call these degenerate modes. Degenerate means the same energy. That's a chemist notation. These are degenerate modes. And it doesn't mean that they're badly behaved, but like some of the people in the front row here. Hey. I'm just kidding. I'm sorry.
I've done nothing wrong.
Degenerate modes, doesn't mean they're degenerates, but rather degenerate and physics means same energy. Okay, and their energy is 539 wave numbers. Okay, so they're very low energy. And of course it's actually fairly easy to chemically rationalize why they're low energy. Right? The stretches are high energy because you're forcing the atoms to stretch their bonds, right, along the axis of the bond, right? You're stretching those bonds. So the bonds are getting longer. That takes quite a bit of energy to break, right? Carbonyl bonds, CO bonds are pretty strong. They're pretty much rock solid. And so it takes a lot of energy to stretch them. So the stretches are very high energy, high frequency, because it takes a lot of energy to move them. But the bends, if you think about it, the length between the C and the O isn't really changing when you go from this to this. Still, my arms are still the same length, but what I'm doing is I'm breaking the conjugation of the two double bonds, right? This molecule is linear because it's stabilized, because all of the p orbitals, all the pi bonds are all aligned. Get a nice conjugation across the chain. But as you move the bonds, you break that, right? You rehybridize that carbon a little bit because you no longer have pure sp2 anymore. And so that, of course, has some energy cost, but it's a much smaller energy cost than it is to stretch a bond. Right? So the bends, in general, bending modes are always lower energy than stretches because the hardest thing to do is break a bond, not distort a molecule. That tends to be a much lower energy process. Okay, so that's a linear molecule. And all of the linear molecules in the world have modes that look like this. They've got stretches and they've got bends. That's it. But I just want to make a quick comparison. Right, just a quick comparison. What if instead we had carbon dioxide? Right? What if we had carbon dioxide instead? Again, it's the exact same isoelectronic. There's nothing different between it except we've changed an atom. Right? But what changes here? Well, when you do a symmetric stretch on CO2, right, CO2 doesn't have a dipole, right? The O's cancel each other out. So all the negative charges going towards the O on one side is being canceled out by the opposite one. Right? So this molecule doesn't have a dipole moment. Right? Because it's symmetric. Right? And so what happens if you symmetrically stretch it? Well, the dipole still doesn't change because you move each oxygen the same displacement away from the center of mass, from the carbon. Right? So the dipole doesn't change. They still cancel each other out. So in CO2, the new 2 mode, the symmetric stretch, is forbidden, which means that it does not absorb infrared radiation. Okay? So the thing I want to, but everything else is precisely the same. Of course, the frequencies change because the carbon-sulfur bond is weaker than the carbon-oxygen bond. So the frequencies will be different. But the only difference between the two molecules vibrationally, really, other than their frequencies, is the fact that nu2 is going to be forbidden because the dipole doesn't change. Okay? So that's a unique thing about these symmetric linear molecules. But in general, all linear molecules vibrate precisely the same way.
But why would there be, I'm confused why there would be no absorption if, maybe I'm just thinking about it wrong. Can you just
Yeah, so the intensity of an absorption is dependent on how much the dipole changes as you move along the coordinate.
Okay.
Okay? So in OCS, if you cut the molecule in half and you ask what's the dipole of CO versus CS, and CS has a smaller dipole than CO because O is more electronegative than S. So this net molecule by itself, without any vibrations, has a dipole moment.
Okay.
Would you agree with
Yeah.
that? Okay. So the fact of the matter is that let's look at the symmetric stretch. Remember the center of mass has to stay constant. And now you're displacing the carbon and the sulfur and the oxygen away from the center of mass, and their displacements are going to be slightly different because this oxygen is half the weight of the sulfur.
Okay.
So every step the sulfur takes in some ways acts twice as much on the motion of the center of mass than the oxygen because the oxygen is lighter. And so that means that this sulfur is going to move, on average, less than the oxygen does. So the oxygen, well, let me just try to draw it. So like in V equals 1, if I draw the carbon in the same place, the sulfur will be at a slightly longer distance, but the oxygen will be much further away than it was in V equals 0. Right? The oxygen displaces more than the sulfur in order to keep them center of mass in the same place. So now the average distance between the S and the O has increased compared to the original place. So now your CO part of the dipole is now bigger than it used to be, and the sulfur hasn't changed that much. So the dipole increases here. Because this bond is getting longer, this one's not changing, so the difference between these two is not 0. So the dipoles, does that make sense to you?
Yeah.
Okay. Right, so that's unique to the fact that we don't have symmetry along this plane right here. We have a sulfur and oxygen. So when you have it just two oxygens, then you get that perfect symmetry along this axis here. The molecule is the same on both sides, so when you stretch along that coordinate equally, you don't get a change in the dipole. Okay? And so when you do SO2, just as a reminder, SO2, that's the molecule in the third rotation. SO2 looks like this. Right? So you can already tell that in SO2 should have 4 vibrations, and you're not going to see one of them. You're not going to see the symmetric stretch by this argument. All right? And the lab report and the data analysis goes through this argument and discusses this in more detail. Okay, so before Sean gets bored, let's move on to a more interesting molecule. All right. What we're going to do for our second choice is formaldehyde. Molecule I've spent too much time studying in my life. All right, and if you don't remember what formaldehyde looks like, it's H2Cl. Right, it's the classic carbonyl molecule. All right, and let's correlate this to a Sean.
This one's a bit more abstract.
Yeah. So Sean's head's going to be the oxygen. Sean's pelvis will be the carbon. And then I'm going to let his arms, since the legs are kind of tricky, to be the hydrogens. Okay? So we'll get him to do a little we'll do some suckets or something like that. That was a bad reference, wrestling joke, I'm sorry. So now the question we have to ask is, how many modes do we have? Right? This is a three-dimensional molecule, it's not linear. So we have 3n minus 6 modes. Right? And there are 4 atoms, so that's 3 times 4 is 12 minus 6, there are 6 modes. 6 vibrations. Okay. And we'll go from top to bottom, like we did before. All right, so new one is what's called the symmetric stretch. All right, and it's at a very high energy, 3121 wave numbers. Okay, and I'll just draw it like this. I'm going to draw my molecule of balls instead of atoms. Just makes it a little easier, right? And the symmetric stretch is described properly. The hydrogens are going to be moving away. And to compensate for the change in the center of mass, the oxygen and the carbon move slightly this way, right? Yeah, there we go. All right, so these got to come out, and then you go right like this, right? A little bit of shoulder action there. Yeah. Right. Now, this number, if you've ever in organic chemistry, if you're given this in organic chemistry and they ask you what kind of vibration this is, the correct answer to the organic chemist would say, oh, this is a CH stretch, because it's at 3,000 wave numbers. And that's precisely what it kind of looks like. Right, the 2 hydrogens displace the furthest. They stretch the furthest, but the important thing is that the whole molecule has to move, because the center of mass has to stay constant in a normal mode in a vibration. So when the hydrogens move away from the center of mass, the stuff on the top of the molecule has to compensate for that, right? Where's the center of mass in this molecule? Probably, let's see, we have 14 and a 16. It's probably right about here. Right, center of mass is about here. Right, so as those hydrogens displace away in what we call a CH stretch, the oxygen also moves. Okay, not by much, right? So this is primarily.
So that's at the center of the formaldehyde. Is that supposed to be an oxygen, or is that supposed to be a C?
Carbon.
Oh, okay, yeah, because I just see the circles. I thought those were all of the names. Just using balls.
No, I'm just using balls and sticks here. Sorry, just to be lazy. Yeah, I'll change that from here on out because it's a little confusing. But this is primarily of what we call CH stretch character, right? That's what an organic chemist would say. Right? We call this a CH stretch, but it's not really a CH stretch. The whole molecule is stretching symmetrically. It's just that the primary motion, the primary displacement, are the hydrogens moving away from the center of mass symmetrically. All right, let's go to the next one. Nu 2 is what we call, is another type of symmetric stretch. We could call it symmetric stretch number 2, but more commonly it's called the CO stretch. And it's a symmetric stretch. All right, and this is the classic CO carbonyl stretch, which if you've ever taken an IR spectrum of a carbonyl molecule, I'm not sure you do an organic chemistry lab or not, but there's usually a really giant, very, very intense narrow peak around 2,000 wave numbers, 2,200 wave numbers, something like that, that's associated with the stretch of the CO. And it's very, very intense. It's almost always very intense because let's consider in formaldehyde, for instance, what's the primary component of the dipole and the charge distribution of this molecule? Well, it's the C and the O, right? The O is that big, massive electronegative species, a bunch of lone pairs, right? And the carbon is largely, right? Remember that carbon is nucleophilic, or sorry, yeah, it's nucleophilic, right? It likes to accept a nucleophile to attack it, and so it's positively polarized, that carbon. So stretching that CO really, really changes the dipole a lot. So these CO stretches tend to be very intense for this reason. I'll just write that. They're just very intense. And of course the CHs are as well, but for a different reason. And so what does this look like? Again, I'm just going to use my ball and stick representation. All right, the CO, of course, this is symmetric, so the O stretches away. The carbon has to compensate by stretching a little bit downwards. And actually, the hydrogens bend slightly inwards or outwards. Yeah, so he has to extend his torso to do this one properly because his torso is the carbonyl bond. Yeah, that's right. He has to. We got to get him on that big torture rack and stretch him like this. Right. So once again, the primary motion of this and the primary motion of the dipole is along the carbon-oxygen bond, but the hydrogens are moving as well. Everything moves along with the main system. And this is at the classic, as I said, it's around 2,000 wave numbers. This is at 2053 wave numbers. Okay. All right. The next set of modes, we start to go down into a different class of motions. All right, so these are the stretches, and we're going to start to get into things where things start to bend. Let me just kind of demarcate these a little bit. All right, so let's do Nu 3. This is what's called the end-plane scissor. And as I said, it's in a different class of energies or vibrations. It's at 1444 wave numbers. Again, kind of small. And it literally is a scissoring motion of the molecule. I'll draw my balls and sticks again. Right, the primary motion is the hydrogen scissor end. Right, we have this bending, rocking motion of the hydrogens. And of course, to compensate for that motion, the oxygen and the carbon have to move away. Right? So, right, you have to kind of go like this, right? Right? Now this mode tends to be a little weaker in terms of intensity because the carbon-oxygen bond, the carbon and the oxygen are kind of moving in the same direction. So the bond length of the CO is not really changing that much. Just this motion of the hydrogen. So the dipole doesn't change nearly as much. Okay, because this carbon-oxygen length kind of stays constant. So I'll write that, the CO bond length. only slightly changes. Right, so it's kind of a weaker transition, weaker spectrum, weaker absorption for this reason. Interestingly, when you look at reactions of formaldehyde, this motion is actually what largely determines most of the trajectories and reactions of formaldehyde, because this pulls the oxygens away and kind of weakens those carbon-hydrogen bonds and pulls them away. And if you imagine that you pull them hard enough, they're just going to come flying off. And that's precisely what it does. When you shine light, say UV light, to photolyze, put enough energy to break apart formaldehyde with a laser, a lot of the dynamics that you see of how formaldehyde falls apart into carbon monoxide and H2, right? That's the primary loss mechanism for decomposition of formaldehyde, is in this carbon monoxide and H2. You find that this motion largely dominates the mechanics, the dynamics, that the hydrogen atoms come together and the CO moves away. Right? You can think of it, right? If you stretch it far enough, you get this kind of, you can break these bonds, the carbon-hydrogen bonds, and form a hydrogen-hydrogen bond, and then you just leave the CO just goes flying away. Right? So this is a very, very reaction-relevant vibration, and a lot of the kinetics of formaldehyde is determined by excitations along this mode. So I'll say this mediates H2CO to CO plus H2 kinetics. You see a lot of new 4-excited formaldehyde when you excite it with a laser, and it starts to decompose. Beautiful, beautiful studies on this. And in fact, there's this really interesting, I don't want to talk about it too much because I'll just sit here and talk about it forever. There's actually this mechanism where one of the hydrogens will leave. In fact, one of them disappears. So like one will break, this bond will break initially. They don't fall so symmetrically. One falls off one. And this hydrogen will roam around. It'll move around the molecule like this, very, very quickly, freely, until it catches and hits that other hydrogen, plucks it off, and flies away. This is called roaming. All right, so it's not just a concerted mechanism necessarily. The two hydrogens come together, bond, and then fly off. This hydrogen will be plucked off and literally traverse and orbit around the rest of the formaldehyde until it catches that other hydrogen and then makes H2 and leaves. All right, it's a roaming mechanism. People finally observed this roaming mechanism in formaldehyde not just maybe 5 years ago, maybe 10. It's been proposed for decades, but no one was able to see it because it's very, very, very fast. The time scale of this roaming is on the order of less than a picosecond, very, very fast. And so it takes very fast lasers to see it. Okay. So let's keep going. Interestingly, in formaldehyde, the next set of modes are degenerate. I won't really talk about why they're degenerate. It happens to do with the fact that formaldehyde has this plane of symmetry here. If I cut the molecule in half, it's the same on both sides. And the fact that if I take the molecule and rotate it 180 degrees this way, I get the same thing back. So you have a rotational symmetry and a plane of symmetry, and those symmetries enforce the fact that you get a set of degenerate vibrations. Right? It's symmetry related. Again, we won't talk about that in class. I certainly will talk about it if you take my spectroscopy course next spring. Dr. Polenko talks about it in Advanced Inorganic. And these are called the rocks. These are the end-plane rocks. And there are two. There is the symmetric and the antisymmetric. And these are really tough for poor Sean. Yeah, I'm going to draw them first, and then we can see if he can interpret them for us.
Did pretty well yesterday.
Yeah, you did do a good job yesterday. So this is the symmetric one. the oxygen and the carbon move in a certain direction, and the hydrogens move in the opposite direction. Sorry, I kind of need to put over there. Right, so, yeah, exactly, just like that, right? Got to do a little Dougie on that one. All right, and the antisymmetric means that the carbon and the oxygen move in opposite directions.
This one's way harder.
And the hydrogens, let me make sure I get it right, move in slightly opposite directions as well. Right, so one's coming down and one's coming up, and then your neck and your, yeah, it's like, ooh, that's a tough one. That's almost like doing the floss, right? You gotta do two different things. I'm gonna stop before I embarrass
Cypher,
myself.
you should do the floss.
No.
I was gonna say, can you do the floss?
I need a demonstration.
Can you
No,
show that
I'm
to
not
the
gonna
class?
do the floss for you guys.
Aw.
Check my TikTok.
It's not on there.
No, I'm
Aw,
just
man.
teasing. And these are both at 1176 wave numbers. They're kind of low energy. All right, and now we're left to the last one, which is very similar to the one we just talked about, but because of the symmetry of the molecule, it's actually not degenerate with the other set, but it is in very close in energy. This is the out-of-plane rock. Which means we're going to come out of the board instead of into the, or on the plane of the board, or out. Sean's going to come out of his plane. So one hydrogen moves out of the board. The other hydrogen moves out of the board. The carbon moves inwards, and the head moves toward. So you're going to go, yeah, exactly. There we go. Beautiful. And this one's, again, it's also a rock. You're kind of moving the atoms in the same direction, but now they're in a perpendicular plane. And that's a slightly different plane than, like, this plane is different than the perpendicular plane. They have different geometry, so you get different energies. But very, very similar. This is at 1165 wave numbers. Okay. So those are our, once you guys finish up, continue up, I'll just talk for a minute. You want to try the cycle of pentane once, too?
I think I'm okay.
Yeah, okay. Let's give Sean a hand for his.
That was educational.
Yeah. So these are the 6 vibrations of formaldehyde. And again, you may wonder, well, why is this important? But the fact of the matter is that the nature of vibrations, in some ways, if you think about atoms and how they react, or molecules and how they react when bonds are broken, when you react two molecules together, they bond and stuff, the way that a molecule flows from one starting material to the product, right, in energy, you can represent this as motion along one of these normal coordinates, right? So as I said, this nu 3, this scissor mode, is very important in disassociation of formaldehyde to form HCO and H2. Right? So vibrational modes and their characters define and determine how molecules react, because these are the natural ways that a molecule will move. Right? These are nice, smooth coordinates that the molecule will move along as you excite them. And so when we see reactions or we see interactions, we have to consider what kind of vibrational state and what kind of motion the nuclei are having in order to consider how they react. Okay, so these are kind of like the unique ways that a molecule can move, right? Not translate, but move internally. Any questions about this so far? Okay. So what I want to show you now, and you guys can just stop taking notes. I don't really need notes on this. I want to show you a bigger example. And then I can't draw all the modes for this molecule on paper, so I'm going to animate them for you instead. And Sean certainly doesn't have enough appendages to do this. So let me tell you a little story. This is a story from my research. I have a colleague from South Carolina, works at the College of Charleston. He's an old organic chemist, very nice Egyptian man. He likes making molecules with silicon and germanium. All right, so silicon and germanium are they're in the same column, the same group as carbon. They're isoelectronic to carbon. And they make carbon bonds. You can make carbon-silicon bonds and carbon-germanium bonds. But the interesting thing about silicon and germanium is because their valence is 3p and 4p, they tend to make very weak bonds with carbon, which has 2p orbitals, 2p valence electrons. We'll talk about those kinds of things when we talk about molecules, if that's not clear to you. But the idea is that silicon and germanium have very similar properties to carbon, but when they interact and bond with carbon, they tend to form weak bonds, floppy bonds, anharmonic bonds. So he sent me this molecule that he made. It's cyclopentane. And what he stuck on it is this is a silicon. This green atom is a silicon. So this is, instead of a methyl group, it's a silane, SiH3. Okay, so I took a spectrum of this molecule. And we don't have to interpret the spectrum so much, but let me show you two things that I noticed in my spectrum. This is from the paper. So anyway, this is not a vibrational spectrum. This is a rotational spectrum. We haven't talked about rotations yet. But every vibrational level has rotations. You can think of each vibrational level of a molecule as a unique molecule. They can all rotate in their own special way. And so here's cyclopentylsilane. This is the molecule I showed you. And he also sent me cyclopentylsilane, but where the methyl, the silane group is SiF3, trifluoride. So we fluorinated this silane. Okay, and the green trace here is my regular molecule, the ground state, vibrational state of the molecule for both of them. You can see there are more lines for the trifluoro species, and that's entirely due to the fact that it's heavier. There's more atoms. The energy levels are closely more spaced because it's heavier and bigger, so you get more lines. But there's really not a huge difference between these two molecules. Fluorine and hydrogen in some ways are very similar when they're bonded to carbon or silicon. Now, fluorines are much more electronegative, of course, but in terms of size and in terms of bonding properties, fluorine's like a heavy electronegative version of hydrogen. They're very similar, right? Because they both have one valence electron. They both form single bonds. They both form strong bonds. But fluorine's a really interesting analog for hydrogen. But anyway, I was looking through the spectrum, and of course, once I assign a spectrum for the ground state, I want to start looking for other weird shit in my spectrum. Anything that might stand out. And what I notice in cyclopentylsilane, in this purple, there are a couple of weak lines that appear in purple here that I assign. And the spectrum for this looks like my ground state, but just slightly shifted. So it's the same molecule. It's some other state of the molecule. But it's the same one. It's not like a different molecule. It's not a mixture. It's some excited state of the molecule. And then I go look at my fluorinated version. Let me scroll down just a bit. And I see the same purple lines, equivalent lines for the fluorinated one, but they're much stronger. Much more intense than they are for cyclopentylsilane. Okay? That was very interesting. I wanted to identify what this is because it's not an impurity. There are various reasons I can confirm that, but I'm 100% certain it's the same molecule. It's just some excited state. And what I want to do is identify the excited state. So my evidence is that I have some excited vibrational state. The spectrum's taken at 1 Kelvin. Right? These molecules are effectively 1 to 10 Kelvin. So it's got to be a really, really low lying state. It can't be in energy. It's not a CH stretch or something like that. It can't be that. It has to be something really, really low in energy. Just as a reminder, 1 Kelvin is 0.7 wave numbers, right? So at 10 Kelvin, you only have 7 wave numbers of energy. So it can't be something at 3,000 wave numbers. You just don't have enough energy to excite it. It's got to be something really low energy. So you might see here on the label, I have something that says nu 48 equals 1. I figure this is the published paper, so I figured out what it is. But let me explain to you what this spectrum is. I have some excited state that I can't identify. So what I did is this. Calculate the molecule, structure of the molecule. This is all computational. Right? It's really, really easy to take one of these outputs and calculate the frequencies, the vibrational modes of the molecule. All right, so let's think about how many modes this molecule should have. It's three-dimensional, so we need to use 3 n minus 6. All right, how many atoms do we have? We have 1, 2, 3, 4, 5, 6 heavy atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. That's 18 atoms. 3 times 18 is 54 minus 6, that's 48. So this should have 48 vibrational modes. And let's look. So here's a list of all of them. I'll scroll down to the bottom and voila, there are 48 of them. Just like I predicted. Okay? And this program, Gaussian, is a program that comes out of, there's a lot of programs that do this, but this is the most common one. Comes from a company in Wallingford. Gives me a list of all the frequencies, of all the vibrations, and as well as their intensities. Right? The intensity tells you how much the dipole changes. Okay, so I know what, I can look at the intense transitions in the frequency. It'll even let me plot a spectrum, which I don't care about here. Right, but it'll even predict an IR spectrum for me, right? This is what the IR spectrum it thinks it looks like. Right, but I'm not doing infrared spectroscopy. I don't really care about this. I just care about the actual states themselves and what the molecule is doing. That's what I'm interested in. But it can certainly calculate the vibrational spectrum. Right, and again, as I said, you have some big stretch here. It's really intense. Here's your CH stretches here around 3,000 wave numbers. Everything that you come to expect from a typical IR spectrum. All right, but the best part of this visualization is I can actually look at how the mode moves. It's going to animate. So let's look at that. So and unfortunately Gaussian sorts them by decreasing frequency, not increasing frequency. So nu 48 is the highest energy, not nu 1, which is really, really annoying, but unfortunately it's beyond my control. So let's look at what these animations look like. So here's the highest energy one. Right? You can see what's happening, right? These 3,000 wave number stretches, right? They're CH stretches, right? The CHs are moving. They're stretching symmetrically in this case. Right? All the atoms are kind of moving collectively, right? This is a classic CH stretch, right? But there are many different ways to move all of these hydrogens, right? And so you can see here, there's a bunch of transitions that all fall, or levels that all fall around 3,000 wave numbers, right? So I can just keep going through them. There's the next one, 47. 46, 45, 44, 43, 42, and 41. Right? These are all the different CH stretches. All the hydrogens on the carbons are all basically the same. The bonds are very similar. And so all of these different unique collective motions of the hydrogens all kind of fall in the same region of energy. That's why when you look at your CH stretch region in an organic molecule IR spectrum, they tend to be kind of broad and kind of spiky, because there's lots of modes, unique modes that are intense that are all overlapping in the region. So CH stretch absorption in a typical organic molecule is not one stretch, but it's actually a collection of many that just all have roughly the same frequency. So I'll keep going. Let's look at 2100, right? So there's some big ass wobbly oscillation of this CH. Right, some more CH stretches in the region. And then you can see, now we have this new class of stretches that are around 2,000 wave numbers, much lower energy. And these are associated with the stretches and the wags of the silicon in the hydrogens, the silane. Right? This silicon-hydrogen bond is weaker than the carbon-hydrogen bond. So its vibrational frequency is smaller because its force constant is smaller because the bond's weaker. Right? So these kind of fall in a smaller, lower energy region. Right? They're uniquely separated from all the other ones. And then as I start to go into the 1500 wave number region, you can see there's tons of lines in this region. 1520, 1498, there's a bunch of them. And these are where we're starting to get our bends and our wags. Right? Just like we saw with formaldehyde, these intermediate ones are associated with these bending motions and these wagging and these scissor motions of the hydrogens. Right? We see very similar properties to the ones here in the cyclopentane derivative. Anyway, I can just keep going, right? Here's some more CHs. But you can see that as I'm starting to get lower and lower energy, the heavy atom structures, the heavy atom skeleton of the ring is starting to vibrate more. Right? We're starting to see oscillations of these heavy atoms where the reduced mass is very large. Right? When you have two large atoms together, your mu is very big, so your frequencies are naturally small. Right? So as we get to lower frequencies, we're starting to see more of these collective motions of the ring. Right? And the organic chemist would call this the fingerprint region. Right? The organic chemist will say all of these collective motions, they all kind of fall in the same region. They're all very complicated. So we just say, okay, this is just that carbon-carbon bend region of your spectrum. We call it the fingerprint. Right? Usually, they always say that the fingerprint has all this rich information but they never analyze it because it's complicated. But that's, in fact, this is where all the interesting stuff starts to happen, in my opinion. Right? And as you can see, as we go lower and lower in energy, the system goes away from moving the really high frequency stiff bonds like the hydrogen bonds, and now we're starting to see more collective motions of the rings, right, of the heavy atoms, and these rocks and these bends. So I'll just keep going. Again, you can see they just kind of fall into energy classes, right? We have some that are at 1300, some at 2000, and now we're starting to get around 900, right? And they all kind of fall into the same kind of categories, right? We can categorize motions by their frequency. Something about their frequency tells you about the kind of motion that's occurring. Right, so now I'm already getting to the bottom. So let's get to the last couple. I think the most interesting ones. Again, as I can see, the trends are the same. The lower the frequency, the more the heavy atoms are moving with respect to each other. Right? We call these the puckering modes of the ring, the envelope modes. Ring structures always have these modes where the rings are going like this. Right? This is how, for instance, cyclohexane chairs isomerize into other cyclohexane chairs. Right? They move along these heavy atom coordinates to go from one chair to another. And I want to show you the last two. So this one at 136, this one looks strange. It's not a heavy atom coordinate. Right? The carbons are barely moving. Right? But it's very, very low frequency. But as you can see, it's mostly just the hydrogens moving. That's a very odd thing, because we saw that the silicon-hydrogen bonds, right, they vibrate kind of around 2,000 wave numbers. But this one's at 136 wave numbers. But as you can see, it's mostly just the hydrogens moving. This is a failure of the harmonic oscillator prediction, because this motion is not actually what's occurring here. Right? This kind of looks like it's going like this. But in fact, what this motion is a rotation of the silane. We call it a torsion. It's actually the SiH3 group rotating by itself. Right? You have free rotation around this bond. So this silane group is going like this. It's torquey. It's rotating like this. And the excitation for that is around 100 wave numbers. But what does the potential for a rotation look like, this torsion? Well, it's sinusoidal. It oscillates every 2 pi, 360 degrees. So you have an oscillatory function, potential. It's not harmonic. It's a sine wave potential. So what this does is it says, okay, I'm going to sit in one of the minima of that sine wave and treat this as a harmonic oscillator, which means I fit a parabola to it. So what you see is this like little bit of angular motion, but in fact what's actually happening is the system is doing this instead. Right? And you just can't see that because you can't fit a sinusoidal potential to a parabola. Okay, so that's a definite failure of this model. Right? And this program actually has ways to identify these torsional modes and to single them out and to then treat them as oscillatory potentials instead of harmonic, right? Which I didn't do here. The last one I want to show you is this one. Now, I don't know if you can see in the back, but this frequency is negative. Well, that's a problem. How do you have a negative energy? And so it turns out that this is chemically a very interesting event. So when you get a negative frequency, what does that mean? Well, remember that the frequency or the stiffness of your bond depends on the curvature of your potential at the minimum. All right? So most of these vibrations are at the minimum of energy, so your potential as you displace looks like this. They're concave up, right? Like parabolas. Right? That means if they're concave up, the second derivative is positive. Therefore, you get a positive frequency, positive force constant. So what does this mean? Well, this means then that the curvature is negative, that you're on a maximum instead. That's what that could mean. But here's the problem. No stable molecule is ever at a maximum of energy. So there are two options here. One is that this calculation is wrong, that it hasn't calculated the vibrations properly because it actually thinks the molecule is on a maximum of energy instead of a minimum. That could be an issue. But there's an important distinction. Look at the magnitude of this number. It's 10 wave numbers, right? So that the sharper the potential, the larger the frequency. So this is a 10 wave number. So this is a very, very, very shallow potential. All right, so I wanted to make sure that I didn't screw something up. I wanted to make sure that this was not a maximum that it's sitting on, but a shallow potential that's so shallow that the program can't determine whether it's positive or negative. Basically, it's flat. It has no curvature at the equilibrium position. That in fact, the curvature should read to 0, and which is just due to numerical error. So what I did is I went and took that motion and followed the molecule's energy as a function of the coordinate and plot the potential energy for it. Let me find it. Here it is. All right, so this is, if you will, the harmonic potential for that negative mode, that lowest energy mode of the molecule. And again, remember, a normal mode is a one-dimensional coordinate. I can just follow all the atoms and plot the reduced coordinate as just one dimension. So it just becomes a one-dimensional oscillator. And here are the potentials for the fluorinated one and this one. It turns out, of course, if you look at these closely enough, you look at this one, it kind of looks like a quadratic function, a parabola. You'd think it was harmonic, but in fact it's not. It's not a harmonic oscillator. You have to fit this to a cubic potential. You need the x cubed term. So this is a very anharmonic potential. You can't fit this to a parabola, even though it looks like one. And this trifluorinated one, as you can see, these are done on the same scale. They're plotted on the same x scale. The trifluorinated one is extremely, extremely shallow. Extremely shallow. In fact, it's probably chorded. It's very, very anharmonic. So when the computer calculates the frequency, it goes down here to the bottom point and calculates what the closest parabolic fit to the function is. Right? It tries to fit this to a quadratic function, and the second derivative of that quadratic function tells you the frequency of the vibration. And when it fits this to a parabola, it's much easier to see here. It fits it to a parabola and calculates the curvature down here at the bottom, how steep it is. It basically says it's not steep at all. It's very, very flat. I wish I could draw it, but the idea is if your potential looks like this, and I need to fit a quadratic to it to do the harmonic oscillator approximation, what's your parabola going to look like? Well, it's going to look something like this. Right? And so, what's the curvature at this point? Well, it's asymptotically flat at the point right down there. It's flat. Right? The slope, right, it's hardly moving at all. It's basically a flat point, right? So this is basically 0, which means that the frequency that it calculates for this coordinate is around 0 wave numbers. All right, and there's some error to it. Right? There's some calculation error that's much larger than that, right? Maybe it's plus or minus 10 wave numbers. Right? This is from calculation. Okay, and so the computer recognizes this. It says, this is a really, really low frequency mode. You should not trust this frequency. It's not that the calculation is wrong. The calculation makes the frequency negative for me, the user, to realize that there's something wrong or problematic with this mode. Okay, so it's not actually a maximum. The potential is just flat. Basically, it predicts a frequency of approximately 0. Because, again, it assumes that it's a parabola. But if the function is not a parabola, it's more shallow than a parabola, then it's going to say, oh, that means the curvature is 0 and it's flat there. So there's no frequency for that motion. And you've got to have some frequency for a motion to occur because there has to be some stiffness to the bond. The only things that have 0 vibrational frequency are bonds that don't exist. Right? So the program tells me that it's negative to say, hey, there's a problem here. All right? So the end result is this lowest lying mode is the excited state that I see in my spectrum. Because it's the lowest lying mode, and the vibrational frequencies that you calculate using this potential, right? I'm actually calculating the real potential and solving the Schrodinger equation for it. So using a harmonic oscillator. Right? So I get the right energies for this. And the energies for this is on, right, the vibrational frequency is on the order of about 15 wave numbers. Now I said our instruments, our measurements about 10 Kelvin, the average energy is about 7 wave numbers. So there's some molecules in my mixture that's in the excited vibrational state of this level. And as you can see, the spacing in cyclopenylsilane is larger than it is in trifluoro. So in order to excite the unfluorinated one, I need more energy. I don't have that much energy, so I don't have a lot of excited molecules in there. But in the fluorinated one, it's much more anharmonic. The energy levels are more closely spaced. It requires less energy to be in V equals 1. Therefore, I see more V equals 1 molecules, and therefore the spectrum is more intense. Okay, and once you do all of this analysis, once I have these potentials, I can calculate anything about this mode. Where it's supposed to show up in my spectrum, what the intensity should be, all of that. And it turns out that once you do this, you get agreement with the experiment to about 2%. All right, so you can really identify these things perfectly. All right, so this is a really important lesson. The harmonic oscillator works, but only works so well. But the nice thing is that the normal mode approximation allows us to decouple problems into one-dimensional problems, which are very easy for us to solve. Okay? Now this might seem complicated, but this is PhD level work, and this is basically fitting things to parabolas and cubic functions. It's not too bad. And you can learn a lot about vibrations this way. Okay, that's all I have for you today. Have a lovely break. Homework's due this weekend. Get it into me at some point. I probably won't grade until, not this weekend, but next weekend. So as long as it's in this week, next coming week during spring break, that'll be fine. Otherwise, have a lovely spring break.
Office hours tomorrow.
Yes.
Is it going to be
in my office?
Okay.